Hello there. In this lesson, we're going to learn about bond energy, which is the energy either required to break apart a bond or the amount of energy that's released when a new bond forms. And so we're going to use these bond energies in order to determine reaction enthalpies because, of course, the energy difference between the two is going to be the enthalpy of the reaction. So in this graph, you can sort of see a little more of how the process, or how you can imagine the process working. First of all, you can think of all of the molecules that you start with breaking apart. In this case, we're doing hydrogen and oxygen to make water. So you can think of the hydrogens and the oxygen molecules all being broken apart. And this, of course, is going to require energy. And so that's the energy being absorbed. So once you've done that, then you get all these single atoms floating around. And then those atoms can come together and form new bonds. And when these bonds form, energy is going to be released. That's what the arrows going out here means. So a certain amount of energy will be absorbed, a certain amount of energy will be released when new bonds are formed, and the difference between them will be our reaction enthalpy. Now, thankfully, we don't have to work out our own bond enthalpies. It's all been done for us. So if you look up in your textbook or online, you can find tables of bond enthalpies, and you see them listed in terms of kilojoules per mole. And so that is the amount of energy either given off when this bond forms, or that's the same amount of energy that will be required when this bond is going to be broken. Now you can see that they're all averages, and that's because different molecules will have slightly different bond energies due to the other atoms that might be in the molecule that might change the nature of the bond. So while this will give you an enthalpy value for any reaction, it might not be quite as accurate as if you did it by calorimetry or Hess's law. Okay, so back to our formation of water here. You can see that the first process is going to absorb energy and call that endothermic. And we can represent that graphically as an increase in enthalpy because energy is going to be required to pull apart those bonds. And so up you go, and you have all these atoms up here that have been separated from each other. And then the second part is when bonds are formed, which is an exothermic process. And so energy is going to be released when that happens. And then the difference then would be the difference between the amount absorbed and released. And so the delta H for this reaction would be negative overall here, because from where you start to where you finish, it's going to be negative. Alrighty, so let's try it with an example. The thing with your examples is you have to be able to figure out how many bonds there are being broken and formed. So methane is this little molecule, if you recall. And oxygen is this little molecule. And water is this little guy. And carbon dioxide is this little guy. So as far as balance goes, let's see here. We need a 2 here. And I think everything else is, no, we need 2 of these as well. Got 4 oxygens, so we need 2 here. Great, so we need another one here, and we need another one here. Okay, so then off of our table, we got to look up the, let's switch colors here. We need the carbon to hydrogen bond. That's this guy. And then we need the oxygen double bond, which is over here. And then we need the oxygen hydrogen bond, which is here. And we need the carbon oxygen bond, double bond, which is here. Oh, the one in CO2 is down here, 799. Okay, so let's work this out. So we got 4 C to H bonds, and we've got 2 O to O bonds. So 4 C to H bonds. The C to H bond's 413. 13. And the 2 O to O bonds, the O to O bond is 495 kilojoules per mole. And this O to H, we've got 1, 2, 3, 4 O to H bonds, which are 467. And we've got 2 C double bond O bonds, which are 799 kilojoules per mole. And this would be like 2 moles, and then it cancels out, and you end up with kilojoules. So let's see what the total amount of bond energy is here and the total here. So my calculator, 4 times 413 is, we got 1652. Then we've got 2 times 495 equals 990. Here we got 4 times 467 equals 1868. And we've got 2 times 799, which is 1598. Now, if you recall, the bond breaking is endothermic, so it's going to be positive, and the bond forming is exothermic, so it's going to be negative. So we'll add these two together. 1652 plus 990 is 2642 kilojoules. And then the exothermic part is 1868 and 1598, which is 3466. So it's going to absorb this much energy, give off that much energy, and so the difference, delta H for this, is the difference between the two. So if you subtract 3466 from 2642, you end up with negative 824 kilojoules. And that would be the enthalpy of this reaction. 824 kilojoules. Great. Another way to do these is with a formula. I still recommend drawing out the little molecules unless you are really good at doing that in your head. You've got 2 elements here that have bonds in them, and you've got 1 molecule, and with the balance you get 2 of those and 3 of these. So then you can use the formula to work out your overall enthalpy. So delta H of the reaction equals 2 times 3, so that's 6 moles of N to H. And then we're going to subtract 1 mole of N triple bond N plus 3 moles of H single bond H. And so we'll look all those up. The N to H bond is here, 391 kilojoules per mole. The N triple bond N is down here at 941, very stable bond, that one. 941 kilojoules per mole. And the H to H bond, where's that one hiding? Here it is, 436. So 436 kilojoules per mole. Okay, so you see moles cancel out, and we're just going to end up with kilojoules once we're all done with this. And so then it's just a calculator game here now. So 6 times 391 equals 2346 kilojoules minus bracket 941 plus 3 times, let's do this one, 3 times 436 equals 1308 kilojoules. And so then we do the whole thing here. So 2346 minus 941 minus 1308 equals positive 97 kilojoules. There you go. A little bit endothermic. Delta H equals 97 kilojoules. That's supposed to be a 7. Great, hope that makes sense. Talk to you soon.